Hi everyone. Welcome to GATE Data Science course. We have finished counting and we will start probability. So in probability statistics in GATE syllabus, there are various modules counting probability. In the statistics, there are random variables and stuff. So I will break down all the components, the entire subject into different modules. And this is the second module of called probability. Okay. And so this is lecture number 1, and we will discuss the basic elements of probability in this lecture, like sample event, sample space, and the different basic axioms of probability. If you have already learned it in you must have learned it in class 10th, 11th, 12th. Okay, so most of the concepts will be same, at least in this lecture. Okay, and then we will move to advanced topics like Bayes theorem, multiplication theorem, and so on. Cool. So firstly, why probability? Why? Because we cannot be sure of certain of outcomes of certain events, right? So what is an event? So basically, whenever you call an event in terms of probability, you will have a universe. So basically, you will be doing an experiment. So the universe won't be the entire universe. For you, for that particular question, for that particular event, the universe will be very confined. For example, you are throwing a die. So when throwing a dice, this is an event, this is an experiment that you're performing. So your universe is confined only to that dice right now. Don't focus on any other thing. You have that universe. That's why we call it universe. Okay, for that experiment, we don't care about any other stuff happening. We just care about what happens when I roll a dice, right? So what is the universe here? You can get a number, right? When you roll a die, it will land somewhere and you will get a number. That is your universe. Okay, so you can get only 6 different options because dice has 6 sides. You can only have 6 different outcomes: 1, 2, 3, 4, 5, and 6. Right? So for that experiment, this becomes your universe. You will get 1, 2, 3, 4, 5, or 6. Right? So this is the universe. And now what is an event? So for an experiment, you define certain events. Let's say for me, for this particular experiment, the event is I want to get a prime number when I roll a die. So getting a prime number now becomes an event. It can happen or it might not happen, right? You're not certain that it will happen. So basically that's where probability comes in. When you're rolling a die, you're not certain a prime number will come or not, right? So what are the prime numbers in 1, 2, 3, 4, 5, 6, 2 and 3, right? So if 2 and 3 comes, your event becomes successful. If 2 and 3 doesn't come, your event becomes a failure. So the notion of probability is how many times do I have to roll in general so that I get a prime number? Or what is basically the probability? That's what probability is, right? What is the probability of getting a prime number? It means that if you roll a die n number of times, infinite number of times, a very large number of times, let's say I roll the dice 1 million times. Generally speaking, I will get 2 by 6 times of 1 million. That's the number. You will get that many times, you'll get a prime number. That's probability, right? So this is also called the frequency interpretation of probability. It means that in general, when you perform an experiment, if you perform an experiment very large number of times, the ratio of number of times your experiment becomes successful, the ratio of the number of times your experiment becomes successful is called the probability of the event. You don't have to roll it 1 or 2 times, right? If you only roll it 1 or 2 times, let's say you roll it only 1 time and you didn't get a prime number. You cannot say that the probability is 0, right? You will get in long term. That's what frequency interpretation says. In long term, if you perform the experiment on a very large sample or a very large number of times, generally speaking, then the ratio, let's say you performed the experiment 6,000 times and you got succeeded 2,000 times, right? In long term, then your probability becomes 2 by 6, right? Very large number of times. Generally speaking, it should be infinity, right? But we have to stop somewhere. So if you perform an experiment very large number of times, then the ratio of your success is called the probability of the event. So consider an experiment. Experiment is our universe whose outcome is not predictable. We don't know what will happen when performing an experiment. We don't know. It's not predictable with certainty in advance. Although the outcome of the experiment will not be known in advance. Okay, so what will happen we don't know. The outcome is not known. Now let us suppose that the set of all possible outcomes is known. We will know the set of all possible outcomes. For example, when we roll a die, we know that the set of all possible outcomes is 1, 2, 3, 4, 5, 6. This is my universe. This is a set of all possible outcomes that can happen. Now this set of all possible outcomes of an experiment is known as the sample space. This is called the sample space of the experiment. Okay, and is denoted by S. So this is my sample space of the experiment. And this kind of experiment is called a random experiment. It is random in nature, right? We don't know what will happen. It is random. Now any subset E of the sample space is known as an event. So any subset, like for example, I told you prime numbers. It is a subset 2, 3. Right? So any subset of the larger set or the sample space is called an event, and it is a set consisting of possible outcomes for the experiment. If the outcome of the experiment is contained in E, then we say that E has occurred. So basically when you do an experiment and the outcome is in E, then we say that event E has occurred, or the event E has resulted in success. Otherwise it is a failure. Okay, I hope you get this. Very basic concept. So like few examples like boy or girl, like generally speaking, the probability of getting a boy or girl is 0.5. So in a large population, this should happen, right? So like you don't know, it will be random, and let's say you're having 3 kids, and like questions might come like if you're having 3 kids, what is the universe? So you can have 3 boys, 2 boys, 1 girl, and so on. This is your universe. So an event can be one of them. Like what is the probability of getting all 3 girls, right? So that's what an event is, and you can calculate probability of that. And rolling a die we have already seen, and you can also roll 2 dice. So these are a few experiments that can be done like in probability, and we will see a lot of experiments during this course. Like we will see a lot more complicated events as well. Cool. Now we will see some elements of probability. Since everything is related to sets, right? This is a set. Everything is related to a set in probability. Like the entire universe is also a set, which is called the sample space. And an event is a subset of the sample space. So now there are a few notations of which are very common. Like these are very common notations known to union like set theory. Okay. So first one is union. For any 2 events E and F of a sample space S, we define the new event E union F. Now E is an event, F is an event, E union F is also an event, which will say that E or F is occurring. Either E or F or both. Anything can happen, right? So let's say again, like you have a sample space of rolling a die 1, 2, 3, 4, 5, 6. Let's say E is the event of getting a prime number, and let's say F is the event of getting an odd number. Then E union F will be what? Getting a prime number or an odd number. So it's like 1, 2, 3 and 5. Okay. So the E union F is called the union of events E and F, and it consists of all outcomes that are either in E or in F or in both E and F. So that's what we did. Just take all the elements in E and F both. So now there is a notion of collectively exhaustive events. Exhaustive means what? So let's say there are 2 events E and F. In rolling a die, let's say one event is getting a even number or odd number. Okay, and another event is getting an even number. Now what happens is their union is actually the entire sample space. If you see, either you will get an odd number or an even number. So first event was odd, second event was even. If you take the union, you will get the entire sample space. In the union, you will get the entire sample space. Right? So what happens? We say that these 2 events, E and F, are collectively exhaustive. Basically, they exhaust all possibilities which can happen in this experiment. Either one of this experiment will definitely happen. Okay, so their union must cover all the events within the entire sample space. So if E union F is S, we say that E and F are collectively exhaustive. Okay, the next concept is intersection. Very simple again. So like again, you can always create Venn diagram and see, right? This is the event E, this is the event F, this is E union F, and the middle region is E intersection F, right? Which is like E and F both. So for any two events E and F, we can also define the new event E intersection F, called the intersection of E and F, to consist of all outcomes that are in both E and F. So again, let's say like E is the event of getting a prime number, and F is the event of getting an odd number. Then E intersection F is what? There is only one element common, right? 3. Getting both prime and odd. Getting both. Okay, sorry, I made a mistake. 5 is also prime here. I should have written 5 as well. Okay, 2, 3 and 5 all are prime. So, yep. Here also you can do this. But here the union will remain same, so it doesn't matter. In union also you should write prime. Okay, 5 is also prime. Cool. So the union remains same, 1, 2, 3, 5. And in intersection, what will happen? Yep. So the event E is getting a prime number 2, 3 or 5. Event F is getting an odd number 1, 3 or 5. What is the intersection of these two? Getting either 3 or 5. Right? Because 3 and 5 are both odd and prime. So, yep, this is called intersection, and it is like saying that both events E and F occur simultaneously. Both are happening. Cool. Here also, like, you should add 5. I said that prime number, right? So in the first slide, okay, you can correct it. Cool. Now there is a notion of mutually exclusive events. We saw collectively exhaustive events. Now there is a notion of mutually exclusive events. What does it mean? Ki two events have nothing in common. That's what exclusive events are. Let's say the event E is getting an odd number. Again, right, see, these two events same. These two events were exhaustive and they are exclusive as well. So how? Let's say E is getting an odd number, F is getting an even number. Now what happens? What is the intersection of these two sets? What is the intersection of these two sets? Nothing. The empty set. There is nothing in common in both these sets, right? So the intersection is phi, or the empty set. So it implies that E and F cannot both occur simultaneously. They cannot occur simultaneously. Then E and F are said to be mutually exclusive events. Okay? Exhaustive, which means that it can be extended to 3-4 sets as well. Let's say 4 events A, B, C, D are exclusive if A intersection B intersection C intersection D is phi, and they are exhaustive if A union B union C union D is S, or the sample space. Cool. The next element is complement. So for any event E, we define the event E complement, and it is called the complement of E, to consist of all the outcomes in the space that are not in E. So if this is the universe, 1, 2, 3, 4, 5, 6, and if E is your event getting a prime number 2, 3 or 5, then what will be E composite? It will be 1, 4 or 6. It is like getting the composite numbers. Okay, it is called the complement event. If you're not getting a prime, you're getting a composite number. So that this is what complement is. Then similarly, you have the concept of subsets. So for any two events E and F, if all the outcomes in E are also in F, if all the outcomes of E are also in F, so basically E is a subset of F, right? So what happens? For we can take an example here. Let's say the event E is getting 2 or 3. Let's say the event F is getting 2, 3 or 5. So here what happens? event E is a subset of F. All the outcomes of E are in F as well. Okay, so we denote it as this, and it says that the occurrence of E necessarily implies that the occurrence of F. So what happens here? If E happens, what does it mean? If 2 or 3 are coming, like if you are either getting a 2 or 3 while rolling a die. So if E happens, F definitely happens, right? Because F says that you should get it 2, 3 or 5. If you're getting a 2 or 3, you are getting a 2, 3 or 5, right? So if E is subset of F, if E happens, F happens. And similarly, if E is a subset of, an event E is a subset of F, and F is also a subset of E, then it will mean that both the sets are actually equal. They are identical. These two events are identical. Okay. So this is like using the Venn diagram showing the same thing. So this is the shaded region here is E union F. Here the shaded region is E intersection F. E intersection F is sometimes written like this as well, EF. Okay, it is E intersection F only. And here the shaded region is E complement. If this is E, this is E complement. Okay. And then we have a few laws as well here. So first is commutative law. These laws are standard in set theory and probability. Okay. So E union F will be equal to F union E. So the union of two sets is commutative. You can do E union F or F union E, it doesn't matter. Then you have the associative law. It means that E union F union G is equal to E union F union G. So when you're doing union, you're anyways taking all the elements in all the sets, right? So it doesn't matter which two sets are you do union first, right? It doesn't matter. You can do E union F or you can do F union G. It doesn't matter. It is associative. And then we have the distributive law. It says that E union F intersection G is E intersection G union F intersection G. It is very easy to see using a Venn diagram. So let's say this is E, F and G. Now it is saying that E union F intersection G. See, E union F is this entire set. And we have to take whatever element which are present in G also. So this area basically. This area is in E union F and it is intersects with G as well. Right? And what is RHS? RHS is E intersection G union F intersection G. So what is E intersection G? E intersection G is this area and F intersection G is this area, and their union is the same area. Okay. So the distributive law also holds in probability, in set theory and in probability. Okay. Now we have a few more Venn diagrams. So here we have Venn diagrams of 3 sets. The shaded region here is common in E and G, so it is EG or E intersection G. Here the shaded region is F intersection G, and here the shaded region is. So it's like proving the same theorem, right? The distributive law which we saw. It's proving the distributive law only. It's drawing the same diagram. Now we have another axiom. What is the complement of E union F? What is the complement of E union F? So again we can draw the Venn diagram. This is E, this is F. The complement of E union F is all the outside area, right? This is E, this is F. The complement E union F is this area. And whatever outside it is E union F complement. So it will be E complement intersection F complement. Basically, whatever. So basically, like, see, you can tell it in English as well, right? E union F is what? E union F is E or F. Something is happening. The complement of it is what? Nothing is happening. Neither E nor F is happening. That's what it is. Neither E and nor F. So basically, E should not happen and F should not happen. Similarly here, what is E intersection F? E and F both happen. E and F both happen simultaneously. What is the complement of that? Ki E and F should not happen both simultaneously. Other than that, everything can happen, right? Only E can happen, only F can happen, none of them can happen. And what is this set? Either E doesn't happen or F doesn't happen. right? Which is correct. What I'm trying to say is, what is E intersection F complement? It is like E and F should not happen simultaneously. It means that either one of them should not happen. That's what RHS is. Either E is not happening or F is not happening, right? Using Venn diagram also you can prove it very easily. Cool. So now we have some axioms of probability. They are standard axioms. Probability of any event can always be between 0 and 1. If you're getting a probability of greater than 1, you are making a mistake. It is not possible. Probability is what, like the ratio I told you of, in long term. If you perform an experiment million times, in how many times your event is successful? If you're performing an experiment million times, your experiment cannot be successful 2 million times, right? It can be between 0 and million. So the ratio can only be between 0 and 1. The probability of sample space is 1. You will always have the sample space. That's why it is called sample space. Sample space is what? The universe. Something within the sample space will always happen. So the probability of happening of sample space is 1. Right? Now there is an axiom. For any sequence of mutually exclusive events, even E2. Let's say we have a few events which are mutually exclusive. It means that all two of them are exclusive. They have nothing in common. It means that they are like this. E1, E2, E3, E4, En. They have nothing in common. They are exclusive events. So we have a sequence of exclusive events. So what will happen here? So the probability of happening of E1 union E2 union E3 union E4 union E5 will be nothing but the sum of individual probabilities. So probability of happening of E1. So basically you can firstly like see it for two sets. It will be easier. If you have only two sets E and F, the probability of union will be probability of E plus probability of F, which is same as cardinality in sets, right? It is same as cardinality in sets. The cardinality of E union F will be cardinality of E plus cardinality of F. So same happens with probability as well. Okay. So there are a few propositions. Probability of E complement will be 1 minus probability of E. So why? Because we know that E complement is nothing but universe or the sample space, sample space minus E. So the probability of E complement will be probability of sample space minus probability of E, which is 1 minus probability of E. Okay. So basically the probability of getting a prime number when we throw a die is what? So the prime number event is what? 2, 3 and 5. This is getting a prime number. Okay, so the probability of E is what? There are 3 cases in which we succeed and there are total 6 cases, right? So the probability of event E is 3 by 6 or 1 by 2. Right, the probability of event E is what? The cardinality of E upon the cardinality of sample space, which is 3 by 6, which is 1 by 2. So in 50% cases your event will be true. So what is the probability of E complement? Probability of getting composite numbers. So it will become 1 minus 1 by 2, which is 1 by 2 again. Okay. And this is the most important law. Okay, this we have seen in, this is standard inclusion exclusion, right? So what happens? If you have two events, E and F, and they are not exclusive, they can have something in common. Then the probability of E union F, we have seen this in set theory as well, right? And also in counting, in counting when we did inclusion exclusion, we saw this. So the probability of E union F will be probability of E plus probability of F. So either E can happen or F can happen. But when we do this, we are overcounting these elements. We are counting them twice. So you have to subtract them once. So it is probability of E intersection F minus probability of E intersection F. Okay. Cool. So let's see an example. A total of 30% American males smoke cigarettes, 10% smoke cigars, and 5% smoke both cigars and cigarettes. What percentage of males smoke neither cigars nor cigarettes? Okay. So there are two types of population given. 30% smoke cigarettes So let's say cigarette is a longer word. Let's say I call them set A and B. And 30% smoke cigarettes and 10% smoke cigars. Okay, and they have said that 5% smoke both. This area is 5%. What does it mean? So the A union B will become 30% plus 10% minus 5%. Okay, A plus B minus A intersection B. It means 45%. No, 35%. So there are 35% people who smoke cigarette or cigar. Union. Now what we want? Neither cigar nor cigarette. None of them, which means the outer set. Basically we want this outer set. So it is basically union, the sample space minus A union B. Sample space is 100% minus 35%. So that's our answer. So total of 65%. And total of 65% people won't smoke cigar or cigarettes. Cool. So there is another concept, a beautiful concept, I would say, in probability. It's called odds in favor and odds in against. These terms are generally used in betting, like if you have seen it. What are odds in favor of happening of an event? Okay, that's a standard term. So odds in favor of a particular event is given by the number of favorable outcomes to the number of unfavorable outcomes. Very simple, like see the formula. So the odds in favor of an event A, odds in favor of an event A is defined to be probability of A upon probability of A complement. So again, like let's take an easy example. Let's say our sample space is 1, 2, 3, 4, 5, 6 dice, rolling a dice. And my event E is getting a 2 or a 3. Getting a 2 or a 3. We know that probability of happening of event E is what? Cardinality of E upon cardinality of S, which means there are 2 elements here upon 6 elements here, which is 1 by 3. The probability of event E is 1 by 3. Similarly, probability of E complement will be what? Probability of not happening of E, which means 2 and 3 don't come, which means 1, 4, 5 or 6 come, which means 4 by 6. Or you can directly use formula, it will be 1 minus 1 by 3, which is 2 by 3. Right? So we say that probability of E is 1 by 3, probability of not happening of E is 2 by 3, and odds in favor of E. Odds in favor of E is what? Odds in favor of E is what? Probability of happening of E upon probability of not happening of E. Which is 1 by 2. So we generally denote it as 1:2. 1 by 2, right? So odds in favor of E is 1:2. It means that generally speaking, 1 times it passes and 2 times it fails. That's what odds in favor mean. In a long term, if 1 time if the event happens, 2 times it doesn't happen. That's what it means, right? Probability of E upon probability of not happening of E. So the odds in favor of E is 1:2. And similarly, the odds against is the reversal of it. Probability of A complement upon probability of A. So the odds against event E is what? Odds against E is the reversal of this, so it will become 2 by 1. 2:1. So odds against is what? Generally speaking, it fails 2 times and passes 1 time. So it's just the opposite. These are just common notations. So we can solve an example. Find the odds in favor and odds in against of throwing a die and getting 3 dots. So the sample space is 1, 2, 3, 4, 5, 6. And the event is getting just 3 dots. This is the event. So probability of E is 1 by 6. Probability of E complement is 5 by 6. The odds in favor of E is what? Probability of E upon probability of E complement, which is 1 by 6 upon 5 by 6, which is 1:5. Similarly, odds in against will be reversal. So odds in against of E is 5:1. So generally speaking, this experiment passes one time and fails 5 times. Okay. There's another question. If odds in favor of Rahul solving a problem are 4-3 and odds against Himanshu solving the problem is 2-6, then what is the probability of Rahul? Okay, so like the event is Rahul solving problem. Let's say the event E is Rahul solving the problem. And let's say the event F is Himanshu solving the problem. Okay, so what they have said ki odds in favor of Rahul solving a problem is 4-3, which means that odds in favor of E are given. Odds in favor of E is given to be 4:3. We know that this is probability of E upon probability of E complement, right? And we know that probability of E complement is 1 minus probability of E. So this is like one equation in one unknown, we can solve it. So if we just pull this here, it will become 4 minus 4 times probability of E is equals 3 times probability of E. Right, I'm just taking 1 minus PE here and 3 here. So this becomes 7 times probability of E is 4. It means probability of happening of E is 4/7. So probability of Rahul solving the problem is 4/7. And the second part is the odds against Himanshu solving the problem. It means that probability of F complement upon probability of F, odds against, which means the reversal, is given to be 2-6. It means that, so you can bring 6 here, this is nothing but 1 minus PF, so it will become 6 minus 6 times PF equals 2 times probability of F. So it means that probability of F becomes 6/8, which is 3/4. So there are 75% chances that Himanshu can solve the problem. Okay. So I'm just using the standard formula and calculating the probabilities. Okay, there is this one question which has been asked in GATE Computer Science, actually 2013. So out of all the 2-digit integers between 1 and 100, out of all the 2-digit integers between 1 and 100, a 2-digit number has to be selected at random. What is the probability that the selected number is not divisible by 7? Okay, so how many 2-digit numbers are there between 1 and 100? They start from 11, 12, up to they go to 99. Okay, and so this is our sample space. Getting a number 11, 12. Okay, they start at 10 actually. They start at 10, right? 10 is also a 2-digit number. So our sample space is 10, 11, 12, up to 99. So how many numbers are there here? The cardinality of S is what? 99 minus 10 plus 1. Right? Whenever you have inclusive sets and continuous, then the cardinality will become 99 minus 10 plus 1. 90. Okay, there are 90 elements, 10, 11, 12 up to 99. And the event E is, so let's say we want to find the probability of getting a number which is not divisible by 7. So the better event to consider will be to get an event which is divisible by 7. That is smaller event, right? So I'm calculating the probability of a smaller event because that's easier to calculate. So let's say the event E is the number will be divisible by 7. Then I will just take the complement. Divisible by 7. So how many numbers in this sample space are divisible by 7? They start at, so 7 is not there. So 14, 21, 28 and so on. Okay, so what will be the last number? 98 will be the last number. 98 is also divisible by 7, right? Okay. So what is the cardinality of this set? It's very easy to calculate. See, up to 100, the number of integers which are divisible by 7 will be 100 by 7 floor. So it will be 14. There are 14 integers from 1 to 100 which are divisible by 7, because 14 times 7 is 98. And we have to remove 1. We have to remove 1 because 7 is not there. 7 is not in the sample space. So there are 13 numbers. So the cardinality of this set is 13. Okay. Now what we want, what is the probability the selected number is not divisible by 7? So we see that probability of event E is 13 by 90. What we want? We want the reversal, like we want the complement. Probability of E complement will be 1 minus 13 by 90, which is 90 minus 13 is 77. 77 over 90. Okay. So this is it. So these are all the basic elements of probability. We saw what a sample space is, what event is, how to calculate the probability, odds in favor, odds in against, and a few axioms and union intersection. Okay, these are all basics in probability. And now we will discuss more complicated stuff like conditional probability, multiplication theorem, and so on. So yeah, like let's go tomorrow. Thanks. Bye bye.